what we do. I'll then give an overview of our architecture and the Graphflow platform. I'll talk about why we chose Spark for our particular use case, and then talk a little bit about the evolution of our architecture, and not just about what our architecture looks like now, but actually how it has changed as our business needs changed and as the Spark project grew. And then finally, where we're going next with Spark. So Graphflow is a platform for recommendations and customer intelligence. We are predominantly for online retail and entertainment businesses. Our system collects data about users and items. Those items can be anything, whether it's a physical product, music, an app, a location, a restaurant. We then collect event data that is related to user behavior in the form of interactions between users and items. These can be a view, a click, a purchase, add to cart, share, like, pretty much anything that denotes a preference between users and an item. We use this interaction data to generate recommendation and predictive models, as well as analytics around user and product behavior. Our system is API-based, so we can collect data and deliver recommendations across channels and devices, and allow our clients to present the right product to their customer at the right time using the right channel. And finally, our front-end applications provide customer insights and dashboards where clients can slice and dice data by time, event type, search functionality, and provide reporting such as funnel, cohort analysis, and A/B testing. The Graphflow platform consists of 4 components. We have the API serving layer, which is responsible for taking data in and serving both recommendations and analytics. We have a front-end application, which is responsible for data visualization, dashboards, analytics, and reporting. Thirdly, we have a data storage layer, which is responsible for storing and indexing raw and aggregate data. And finally, a computation layer, which is responsible for generating recommendation models as well as analytics and data aggregation. And that's where Spark comes in. So why did we choose Spark? Well, with its in-memory caching and broadcast variables, Spark was the obvious choice for machine learning when we started to build Graphflow. In addition, the fact that it has APIs in Scala, Python, and SQL was a big win for us. And in particular, the Python API is important for our team, as not everyone knows Scala, and new hires are actually very likely to know SQL and Python, but not necessarily Scala. We also use Shark and the IPython console heavily for exploratory analysis and data visualization. So again, the Python API is a big win there. And Spark Streaming provides the potential to move to online learning and model updates, as well as real-time aggregation. More recently, MLlib, together with Python libraries such as scikit-learn, gives us a rich tool set for developing and testing new models. And Spark SQL allows us to streamline our SQL-based jobs and remove the complexity of having a separate Shark and Hive installation. So the first stab of our architecture looked like this. We decided to go with a graph database for our data storage layer. The reason behind this was that graph database was a natural fit for our data model, where we have many different types of objects. We have the connections between those objects and arbitrary properties that we can attach to both the objects and connections. We went with Titan, which is a distributed graph database built on top of either Cassandra or HBase. So we got all the power and flexibility of a graph database model, as well as the inherent scalability of these NoSQL data stores. We would run recommendation models directly on the data in Titan and store the pre-computed predictions back into Titan for the serving layer. We would then periodically dump data from Titan into S3 and Shark tables and run Python analytics jobs using the Thrift client to compute analytics and aggregations and dump small amounts of aggregate data into the SQL layer for serving via dashboards and front-end reports. So now that we had the data in Titan, how do we get it out from Spark? How do we compute recommendations? How do we do some interesting stuff? Well, Titan was designed for OLTP, and it's specifically optimized for local traversal of a graph, not whole graph traversal. So Titan comes with Faunus, which is a DSL that is designed for parallel breadth-first traversal of the entire graph using Hadoop. So our Hadoop-based pipeline would look something like use Faunus to pull out the data, filter it, maybe transform it, store that as sequence files in HDFS, then run a Mahout-based multiple job workflow to compute recommendations, and store that data back in Titan. In contrast, Spark is fully compatible with Hadoop and any arbitrary custom input format. So all we did is plug in the Faunus input formats into Spark, do all our aggregation and recommendation computation within Spark, and store the data back in Spark. So we had one app. The entire pipeline was one app. You can see here the similarities between the Faunus DSL, which has filters and projection methods, and the Spark API. So the natural Spark API out the box gave us a very similar functionality to a DSL. So what were some of the challenges that we faced roughly a year ago when we started building all of this? Well, Spark was relatively less mature than it is now. It was at around 0.7. So there was no MLlib. We had to write our own. So we wrote a port of Mahout's alternating least squares collaborative filtering model using Spark and Breeze. There was no job scheduling, no job server. So again, we had to write our own. We wrote a Scalatra REST API and Akka-based job server, which is essentially a simpler version of the one that was open sourced by Uyala at the end of last year. So we ran a few small experiments to compare our custom Spark ALS model to Mahout's. This was run probably around September last year using Spark 0.8.0 on the movie lens 1 million dataset implicit preferences. So we saw significant speed-ups of about 6 times just using a pretty naive port from Mahout's implementation into Spark. And in addition, it's a lot more concise, significantly less code. To give you an idea of that, here's a comparison of the implicit update function in the ALS model. On the left, you have Mahout, and on the right, our custom implementation. I've highlighted in purple areas where we're doing matrix vector multiplication, and in orange, element-wise operations. So you can see that the Scala and the combination of Scala and Breeze is a big win for having concise, clear code, and it was still extremely performant. So what were some of the architecture issues that we ran into with version 1? Well, we ended up not using Titan's very powerful features. It's a fantastic piece of software, but we found that actually search, filtering, and aggregation functionality was a lot more important than local graph traversals. Now, Titan supported Elasticsearch and has built-in support for indexing data in Elasticsearch and using it within Titan. But essentially, we wanted to index everything and make everything searchable, so that resulted in duplication of everything. So we'd have to have all our data in both Titan and Elasticsearch. So the complexity of running both just really didn't make sense. And the second one was that we had always known that exhaustive pre-computation of recommendations was going to be very inefficient, and it didn't support incremental model updates. So we wanted to move to much more real-time serving of our models. So we switched things around, and this was the second version. So firstly, we replaced Titan and HBase with Elasticsearch. We replaced the combination of Shark Server with Python and Thrift with Spark SQL. And thirdly, we created our own model server, which served real-time models. And finally, integrated MLlib into our model pipeline. In the future, we may actually completely replace the SQL serving layer with Elasticsearch for aggregations. So as a result of all of this, we saw a huge boost in speed and flexibility. But now we had replaced our entire data store, so we had to, how does that impact our Spark jobs? Well, all we had to do was change a few lines of code. We literally just swapped out the input formats and added some configuration. So that was a big win. We didn't have to change anything else. As a result of this, we also got full access to the Elasticsearch Query API, which effectively gave us very powerful push-down predicates, time-based filters that we could apply when pulling data, so before we even analyzed it. So that was a big win. But we could still use Spark for anything that was more complex, joins and complex aggregations. So integrating Spark SQL was just as simple. Now that we had a custom RDD from our custom input format, we could mix and match Spark and Spark SQL. We can use Spark for more complex joins and filters, and we could literally just copy and paste our Hive query language statements from our Python jobs into Spark SQL and still use all the custom standard Hive UDFs that we were using. Integrating MLlib into the pipeline resulted in significant speedups. MLlib's ALS implementation is a lot more efficient than our initial fairly naive implementation. So this was, these are the timings on the same experiment that we ran previously. And again, we're getting another 2 times speed up over our implementation. It is a little bit more complex, but the model is a lot more complex than the algorithm. Should note that these results are from around Spark 0.8.1, the last time we ran this experiment. So recent MLlib improvements should have made this a lot faster. So the final component that we needed to put in place was the model server for real-time serving of predictive models and recommendations. Now, our requirements were that we needed to serve hundreds to thousands of concurrent models. We have many, many clients, multiple potential models per client. We had the situation where we would have many, many small models, sometimes only tens to hundreds of thousands of users and items, but a few very, very large models, so it could be up to millions of users and items. It needed to be very fast because we're introducing another layer, another round trip here over HTTP, and recommendations is the most compute-intensive operation that we perform in our product. So effectively, client page loads and application performance depends on how fast we can deliver a response. So we looked at a couple of, and finally it needed to be horizontally scalable and fault tolerant. So we looked at a couple of alternatives that are out there, and none of them really fit. Oryx from Cloudera is a really fantastic system for serving one model. It had no Spark integration and wasn't really designed to serve the thousands of concurrent models. Prediction.io was another one that we looked at, but that was, it was nice that it was in Scala, but it depended on MongoDB, and it was Hadoop-based with no Spark integration. And finally, we also needed support for custom models, ensembles. We wanted to mix and match collaborative filtering with other types of models, and none of these really did the trick. So we designed our own. So the data flow is pretty simple. We're pulling data from Elasticsearch into Spark and computing with Spark and MLlib the models, saving those models to S3, which are time-stamped, and then the model server is periodically refreshing from S3. The model server itself is a Scalatra REST API front-end. We built everything based on Akka, so we're using the Akka clustering, and models are sharded across nodes, which gives us the horizontal scalability we need and the ability to handle thousands of concurrent models. We're using Breeze for linear algebra and computing all the predictions. Akka scheduling infrastructure for scheduling periodic model refreshes from S3, and working currently on incremental updates, which will be effectively mini batches, and together with that, caching of results. So in recommendations, some results don't really change very fast. So for example, related products or similar items tend to change relatively slowly. So you can get away with caching those results, which can give huge speed ups in the case of very large models. So that brings us to now, mid-2014. What are some of the challenges that we're facing using Spark now? Well, the ecosystem has matured significantly. We're at Spark 1.0 now from 0.7 when we started out. We have MLlib, we have a job server, we have Spark Submit for submitting jobs. So adding different jobs and aggregations is now very easy. Adding new models, new types of models is a bit more complex, but the combination of Spark, MLlib, Breeze, scikit-learn gives us all the required primitives that we really need for this. So our main challenges now have actually switched to things like DevOps and deployment and job scheduling and automation, which are still, it has improved a lot, but are still pain points. So for deployment, we run everything on Amazon, so we use the EC2 scripts, which are pretty good. For job scheduling, we've tried out the job server, Spark job server. We've looked a little bit at Kronos. We're looking at Azkaban. To be honest, we haven't really settled on an answer. At the moment, we find the ability to schedule periodic jobs and have a really good overview of what jobs are executing to be really valuable. So Azkaban is at the moment sort of out in front, but we are using the job server a lot too. And then finally, and related to that is job automation. We want to be able to dynamically schedule jobs as new clients come on board, as we deploy new models. We want differing schedules based on the data velocity that differs between clients. So these are some of the challenges that we're looking at and working on at the moment. So where are we going in the future with our use of Spark? Well, in the near future, we're looking at more complex models using Spark. So new types of recommendation models, ensembles, combining collaborative filtering style models with other models, adding in even more data, so as much data as we can get around user and item metadata, contextual event data. We're looking at different types of predictive models, so using some of the MLlib functionality around clustering for things like segmentation, classification for things like churn modeling, potentially fraud detection. We're looking at incorporating Spark streaming for both online model updates as well as incremental aggregations into Elasticsearch. And then finally, more complex and compute-intensive aggregations for reporting and insights. So trying to slice and dice the data in more interesting ways and highlight segments of customers or clusters of products that are under or overperforming, for example, slicing and dicing data by various variables, by geolocation, so a lot more sort of intensive aggregations. And then in the more distant future, we're investigating using Spark streaming for online model updates. So instead of rerunning computations every so often and having the model server itself perform model updates, we'll stream data into Spark streaming and have the model updates performed there, as well as using Spark streaming potentially to aggregate in real time and then store those aggregations back into the Elasticsearch layer for serving and search. That's it. Thank you for your time. If I'm around for the next few days, if you're interested in chatting about Spark, I would love to catch up with you. Yeah, any questions?
Thanks a lot, Nick.
What techniques would you like to see added to the library for recommendation engines?
Sorry, could you repeat?
Sure. What specific techniques beyond ALS would you like to see added to the library?
For MLlib? That's a great question. I think that there's a lot of interesting stuff happening at the moment in recommendations, particularly around how to model contextual data and how to incorporate side information. So instead of just taking only the user behavior data, the user item matrix effectively and performing collaborative filtering, there are a lot of techniques that you can use to, in a similar vein, to add context data. So for example, important context might be geolocation, time of day, and also combining content-based filtering, so effectively user and item metadata, for example. So what we're really moving towards is a holistic model that will incorporate both collaborative filtering and kind of user behavior with contextual data around each event with item and user metadata. And I think there you're effectively going to be combining collaborative filtering style models with some online gradient descent style models. So I think being able to do that in MLlib would be great. We haven't explored exactly how to do it yet, so I'm not sure if things will need to be added. But obviously, that's our focus. So we'd like to see some of these more complex, contextual or context-aware collaborative filtering models come in.
This model server seems extremely useful. Is it open source? Are you planning to do it? I think it would be really good.
We've just created it, so as of now, it's still a bit rough. It is in production, but it definitely needs a bit of work. And while it's designed to be sort of fairly generic, it is quite sort of specific to our use case at the moment. So the short answer is I don't know. I think that it is something that is effectively generic enough, or can be made generic enough, that it would be a great addition to the ecosystem. So I'll let you guys know. It'd be nice to open source it, but at this point, I'm not ready for that.
Yeah. So with the second architecture that you showed, are you basically no longer doing like are you evaluating all the recommendations sort of at request time rather than doing pre-computed?
Yeah, so it's fully real time now, with the caveat that there's a little bit of caching. So as I said, especially if you move to sort of incremental updates in mini batches. So for example, Oryx, I've looked into the incremental updates there, and we'll be implementing something quite similar. But effectively there, with each event, you're kind of updating the model. And I think it's probably a slightly better idea perhaps to do mini batch updates where you're doing it every few events, every 10 to 100 or whatever the case may be. So if you're doing that, you can actually get away with, in the meantime, caching results. That's particularly useful for when you're getting things like similar or related products, because that's sort of one of the most common calls that is made.
Sorry, quick follow-up question. So like if you have like a customer that has 1 million items or whatever, and like a request comes in for give me items similar to item A, are there any like particular tricks that you do so you don't have to compare? Like, so you don't have to compare it to every other item to get the 10 with the high score?
Yeah, so naively, that's exactly what you have to do. So for you point out as for very large item sets, that's a problem. So the two ways that you can normally get around it is either using some sort of approximation, like a locality-sensitive hashing, something like that, to reduce the search space, or you can parallelize that. So we found that unless the item space is extremely large, Breeze is pretty fast, so we can get pretty decent response times. But at the moment, we are looking for the larger item sets at one of those two approaches, potentially both. But I think either of those could work.
Okay, thank you.
A couple of questions. So first of all, how do you evaluate the models? Is there a A/B testing mechanism, something like that, for evaluating models? And also, how do you find the right trade-off between complexity of the model? So maybe in some cases, just a model based on item to item is enough for a user. Let's say just take the last few items the user purchased or viewed, and then like give them some weightage versus a full collaborative filtering model. How do you evaluate those trade-offs? Some of it is not fully relevant to Spark.
Sure. Yeah, I think that's a sort of a general problem in any data science. So you effectively can do some offline evaluation as well as online evaluation. So the offline stuff is pretty standard, cross-validation using some sort of metric. We're dealing a lot with implicit data, so effectively things like average precision or mean average precision, or expected percentile rank. These are the kind of metrics that you typically use to try and see how well you reconstruct the data set. But obviously, mapping that to the real world is a little bit more tricky, because there's some tricks that you can apply to real world recommendations that might actually decrease the offline performance but are better for online. So we have a sort of multi-level A/B testing framework in place where we provide a sort of split test for both our model and a baseline, so we can show clients how well we're doing. But we also have within that we can perform multiple split tests internally, so we can deploy different types of models. So we did that recently where we had our standard model and then we had a slight improvement. We deployed that on 50% of the data, and we just compared the results and saw that new model was working well, the tweaks we had made, and then we deployed it fully. So that's really it's kind of the best you can do. You can get as good a model as you can on offline evaluation using the standard cross-validation tools, and then deploy it in the real world, but always keep, everything should be A/B tested, everything should be split test. Always keep the ability to tweak your model, to maybe try different parameters, to try different versions of the model. You could try, for example, a full collaborative filtering model versus a more one based on recent history versus a co-occurrence model, and actually see which ones perform the best. And then obviously there you're not measuring some evaluation metric which is based on the maths. You're actually measuring how well does this result in uplift of average revenue per user, average basket size, customer activity. These are the kind of things that are relevant in the business context that you want to measure in your online testing.